In the previous video, we saw that this object is undergoing an elliptical orbit in the clockwise direction, and it has semi-major axis 3, semi-minor axis 2, and we're asked to find the velocity vector as a function of time. What shape does it describe? Let's take a look. I know, just looking at this motion, that the particle starts out going this way, later it's moving that way, later this direction, so we expect a similar kind of shape here, but describing the velocity vector. To find that, I'm going to take time derivatives of these two functions. Remember, if I look at a function like sine, begins this way, and I note that it has a maximum slope to start, but that slope starts getting smaller and smaller. So looking at the derivative, the slope is getting smaller until it reaches 0, where we have a flat spot on the original function, and then it reaches a maximum negative value at this point, where the magenta function sine has reached a maximum negative slope and comes back to 0 when we reach another flat point. So I see the derivative of sine is cosine. So v is a function of t, it's a vector function. The x component, I hat direction, is the time derivative of this, which is derivative of sine is cosine. We had sine of 2 pi t, so we're going to have cosine of 2 pi t. Now an important thing to note is that the coefficient of t here is what determines how rapidly this function oscillates. The higher this number is in front of t, the more oscillations I'm going to have per time. Let's take a look at how that looks in Desmos. So here I have y equals 3 times the cosine of 2 times pi times x. But let's imagine instead of 2 times pi, we're going to have some number w there. Notice that if I make w bigger, I get the same shape, but it's shrunk. So what's that going to do to the slope at every point here? Take a look at the slope. At the first point we cross the y-axis, notice it becomes steeper. So what that means is we need to multiply the derivative by this coefficient that's inside. You'll learn soon in calculus that this is called the chain rule. The derivative of the cosine of x is the sine of x, but then times the coefficient that's inside, so times the derivative of what we have inside. Let me shrink that down so you can see it. So notice as I change w, I'm making more oscillations per second in the red function, and that means I have a faster rate of change. We can see that with our spring system. Faster rate of change for the velocity. And the peak velocity has to increase. So our red function here is representing the position, blue function is representing the velocity. Moving back to our problem set, this means that Vx is a function of t, it's the derivative of this x term, so I have 3 times derivative of sine is cosine, so this is going to be 3 cosine of 2 pi t times the derivative of what is inside for the reason we just explained, so 3 times 2 pi times cosine of t. Looking at the y component, the derivative of cosine, since I start at a value that's positive and the slope gets more and more negative, we see that the derivative of cosine is negative sine, so this has to be minus 2 times the sine of 2 pi times how many seconds have gone by, and again we have to multiply by the inside coefficient, 2 pi. Simplifying that, I see that this is 6 pi cosine of 2 pi t in the x direction minus 4 pi, 2 times 2 is 4, sine of 2 pi t in the y direction, that second term, so j hat. That is our v of t function. So notice this still has the form of an ellipse. I have a component that is going like not sine and cosine, but cosine and sine. And this shape has an amplitude of 6 pi in the x direction and 4 pi in the y direction. So we see that this is a very similar shape. It's an ellipse with an aspect ratio of 3 to 2, just scaled by a factor of pi. So the shape of this velocity vector as a function of time, it describes the same shape. The velocity vector's point is going to move around in an ellipse, just like this. but scaled by a factor of pi. Part C, we're asked to find the acceleration vector, show that its direction is along r, that is, its radial. This is just the velocity, the derivative of the velocity vector, so acceleration is a function of time. Applying the same rules, derivative of cosine is negative sine, and we need to multiply by the inside coefficient. So this is going to equal 2 pi times 2 pi times 3, that is 12 pi squared. Derivative of cosine is negative sine, so we have negative 12 pi squared sine of 2 pi t minus, here we have 2 times 2 pi times sine of 2 pi t. We need to remember that the derivative of sine is cosine, so the derivative of negative sine is negative cosine. But what is the coefficient? It is 2 times 2 pi times 2 pi. That's 2 times 2 times 2 is 8 times pi squared. 8 pi squared cosine of 2 pi t. This is in the I hat direction, our first term, and in the j hat direction, the second term. So this is the x component is given by this expression. The y component of acceleration is given by that expression. And show that its direction is along r, that is it is radial. So is this function a multiple of our function for r as a function of t? Let's see. Well, the x component is proportional to sine of 2 pi t. The y component is proportional to cosine of 2 pi t. And I see that that same thing is true for r. So what we've seen is that this function is, let's see, we move from 3 to 12 pi. So this is equal to 4 pi. And whereas I started with a positive sine as a function of 2 pi t, now I have a negative sine as a function of 2 pi t. So this is negative 4 pi times our vector r as a function of time. So that proves the acceleration vector is negative a constant times the position vector, which is radial. So we see that the acceleration is indeed radial, or always toward the center of this orbit.